Okay, so in this video, we're going to go over the thermodynamic principle of entropy. So up to this point, we've kind of been doing more of the calculations-based heat calculations on the thermochem side. And so this is definitely more on the thermodynamics side. So entropy is the dispersal of matter and energy in a system where the state of having more dispersal and or more disorder is the more favored state. And that is represented by a positive value of entropy, which is the variable S. So this we would say is a positive delta S. Okay. So kind of the way I like to explain entropy and the way I explained it in class is like my house is a two-story house. My master bedroom is on the bottom floor of the house, and my two sons live upstairs, and they are 12 and 8. And so I try to avoid going upstairs at any and all costs, right? Because inevitably it ends up with mom yelling and the boys stomping around angrily as I force them to clean up the disgusting pigsty that is their area upstairs. But inevitably, every 2 weeks or so, I go upstairs and this, yelling and stomping and cleaning ensues. And it takes them like forever to put everything away, to put all the laundry away, to put all the books away, to put all the everything that they have gotten out away. And then they call me to come upstairs. Mom, it's clean. And I come upstairs and I check and it's clean or at least livable. And it feels like that before I get to the bottom of the stairs, it's all over the place again. And the reason is because of entropy. Okay. The universe favors disorder. The universe favors a high degree of entropy. It is the more favored state. It is the thermodynamically favored state. Disorder is favored by the universe compared to order. Another way you can look at it is it takes you energy input to organize your junk. It takes no energy whatsoever for it to go all over the place. So having a lot of disorder, the positive delta S state is favorable, and having organization, the negative delta S state, is unfavorable. Okay, so kind of just an analogy that'll hopefully help you figure this one out. So entropy can be examined both qualitatively and quantitatively, meaning by description and by calculation. And so we're going to look at the description portion first. So qualitatively, I have 3 boxes. So the red, burgundy, whatever color we want to describe these circles in the boxes, are different states. We can see that in box A, my molecules, my atoms, my particles, whatever they are densely packed, very ordered, organized in lines and rows. And in box B, they're more spread out, seemingly randomly. And box C, they're closer together than B, not nearly as close to A. Well, if you think about these are representative of your states of matter. So what state of matter is A? My molecules are packed together tightly, closely touching. This is a solid. All right. C, kind of close, not as close as A. This is a liquid. And then B is a gas. Okay. And if we were to compare the entropy in each of these samples, we'd say that B has the highest degree of entropy. These molecules are most disorganized and most dispersed. And A, our solid sample, has the least amount of entropy, as those molecules are packed tightly together and are highly organized. Okay? And then C is going to lie somewhere in between. It's not going to have as high a value as B, but it will for sure be higher than A. All right, so we're going to look at some hints that'll help you make qualitative comparisons of entropy. So we're going to look at the states of matter in a reaction and then what that would cause the sign of delta S to be. So If we consider this to be a reaction, that means that what's on the left of the arrow are reactants, what's on the right of the arrow are my products. If I have reactants that are solids and products that are liquids, did I become more or less disordered? Well, I went from tightly packed to more spread out, so my entropy would increase. So the sign of delta S would be positive, again indicating more disorder or dispersal. In the next example, if I have liquid reactants and they're producing gaseous products, I'm going from a more condensed to a much less condensed state. So my amount of disorder is increasing. So this would also be a positive delta S. If I'm going from a liquid state to a solid state, I'm going from a more dispersed to a less dispersed organization. The sign of delta S would be decreasing. So what would be maybe an example of all of these? Going from solid ice to liquid water, right? I'm going from my pretty organized state of the solid ice where my molecules are held together quite tightly to a more flexible liquid state. If I'm going from liquid to gas, so boiling my water, right? As I boil it, I put energy in, the molecules speed up, they're going to move around more, positive delta S. Going from a liquid to a solid, so this would be the opposite way. This would be my liquid water freezing into solid ice, more organized. If I go from a gas to a liquid, again, more organized. This would be like water vapor as it condenses. So we go from the gas state to the liquid state. Okay. Solid or liquid to an aqueous solution. Remember that aqueous means that we have ions in solution, free-floating ions. So if I go from something that is solid into ions, or something that is combined as a liquid into ions, I'm going to at least be breaking one thing down into two or more things. So this is going to have an increase in my level of entropy. So a good example of this would be like if I had solid NaCl, right, table salt, and I put it into water, we know that that means that the NaCl would come apart into Na plus and Cl minus. And so I've gone from having one thing to now having two things, two ions in solution. So it's going to be more disorganized. If I go the other way, from an aqueous solution down to liquids or solids, I'm going to be less disordered. I'm going to be more organized. I'm going to be more condensed in my state. All right. Now, if everything is made of gas in my reaction, my rules are going to become a little different because of the nature of gas molecules. So let's go back to our picture for just a second. So in our gas molecules here, it doesn't matter what the chemical identity of those particular particles are, right? They're bouncing around together. It doesn't really matter, right? So if I took half of these and colored them in blue, or two of the five colored in blue, right? They have a different chemical makeup, but they're still just bouncing around. And so when I look at gases, because of the way that they bounce around, I have to look at the number of moles of gas in my reaction. And I just need to see if the number of moles change. Because if the number of moles stays the same, I still just have the same amount of things bouncing around. But if my number of moles increase or decrease, then that's going to change what I have in my container. So if I look and my number of moles on the left and my moles on the right is equal, then there is no change in my entropy. If I have more moles initially and then they rearrange into less moles, then I'm going to have a more ordered state. If I have less moles and they rearrange to make more moles, I'm going to have a more disordered state. So I'm going to kind of turn this a little sideways for a second, and I want to do at least one example of this so you can see what I mean. So let's just bear with me here as we go kind of crooked. So if I have the reaction 2N2O4 gas, and I go to 4NO2 gas and O2 gas. What I mean by talking about the moles, let me zoom in here just a little bit. All right. On my reactant side here, I have the coefficient of 2, so I have 2 moles. On the product side, I have 4, and then I have the invisible 1, so I have 5 moles. So I'm starting with 2 moles, and I'm going to 5 moles. So my disorder is going to increase. This would have a positive sign for delta S. I still have this reaction. What's just happening is because the way I've rearranged my 2 moles, I've split it apart, and now I have 4 NO2 and 1 O2. I just have more things that are bouncing around in my container. All right, so that's what I'm talking about a rearrangement. All right, so let's zoom back out. So those are my qualitative examples. Let's talk about now some quantitative examples. How do I calculate this if I'm given numbers? All right, so qualitatively, we can say we are going to calculate delta S, or what I have here is called delta S naught, where this little circle is pronounced naught, and it represents that the reaction is occurring at standard conditions, which for the purposes here are 25 degrees Celsius. So if I just showed you the delta S without the little circle, that would be delta S that was occurring potentially at any temperature other than this. But if it has the naught, then automatically I know it's 25 degrees Celsius. All right. So I can use this equation both with and without the little naught, guys. So our equation here is that the delta S of the reaction is equal to the sum. This little sigma, weird looking E guy, means the sum of the delta S of the products minus the sum of the delta S of the reactants. So I have to look at the products and subtract the reactants. So this is our example. 2SO2 gas plus O2 gas yields 2SO3 gas. So looking at it first, let's look at it qualitatively and see what, according to the rules that we just used, what we would say. So I've got gas, gas, and gas. If it's all gas, I need to consider moles. So I have 2 moles and 1 mole. So this is 3 moles, and I'm going to 2 moles. So if 3 moles going to 2 moles, it's getting less disordered. So I would expect the value of delta S to be negative, meaning it's not favorable. It's not a favorable condition. It's not thermodynamically favorable. All right, so let's look at how this works. So these values here come from a standard table of entropy values. When you're doing problems, they would have to be given to you, or you would have to have a means of looking them up. A lot of times, worksheets now will have like a QR code you can scan that'll bring up a table of these particular values. But for our purposes, I've given them to you. So we're going to run through how to properly calculate this. So delta S naught, again, tells me that we're at 25 degrees Celsius, is equal to the delta S of my products. So my products are 2SO3. So 2 times the value of the SO3 that was given, 256.6. All right, and that's all I have for products. If I had more products, I would add them to what I have going on here. But because I only have one, that's it. I'm going to close my bracket. Minus, and I'm going to open a new bracket for my reactants. So I have 2 reactants. I have 2 SO2 and I have O2. So 2 times the value of the SO2, 248.1, plus 1 times the value of the O2. So I'm just going to write the O2 in, 205.3. And then I just calculate, right? I'm just going to do the math part. I'm going to add it up. So I'm going to multiply here and add. I'm going to multiply here, and then I'm going to subtract the difference. And when I do that, delta S naught of the reaction is equal to negative 188.3, and then my unit here is joules per mole Kelvin. We haven't talked about Kelvin yet. Kelvin is a unit of temperature. To relate Kelvin to Celsius, Kelvin, which is absolute temperature, is defined as taking your Celsius temperature and adding 273. You won't need that until we start doing Gibbs, but that's just where it comes from. So it's the Kelvin temperature comes from your Celsius plus 273. So negative 188.3 joules per mole Kelvin, which is good because it agrees with the fact that we said this would be negative. All right, let's do one more. So we've got 4S solid, or 4Fe solid, plus 3O2 gas, and we're going to make Fe2O3 solid. So is the delta S going to be positive or negative, would we assume? Well, I've got a solid and a gas, but they're coming together and making one solid. So I had a gas, I got rid of it. I had two things, I combined it into one thing. I'm going to say delta S is probably going to be negative here. Okay? So now for the math. Delta S naught of the reaction is equal to my products. So 2 times the Fe2O3, which is 90, minus my reaction 4 times the 27 plus 3 times the 205.3. All right. So mathematically, I'm going to multiply my 4 and my 27. I'm going to multiply my 3 and my 205.3, add that together, and I'm going to subtract that from the 2 times 90 that I get here. And so that's going to give me delta S of my reaction equal to negative 544 joules per mole Kelvin. And then it's negative. So kind of summarizing this, the positive delta S is my favorable, thermodynamically favorable, right? Another way to say that is if we say it's spontaneous, is a positive delta S, right? Like my kid's messy room, happens all by itself. My negative delta S, my organized state, is my unfavorable condition. So before we go on, I do want to kind of spiral back and relate these to what we were talking about with delta H. So we had two conditions for delta H. We had a negative delta H, which was exothermic. We had a positive delta H that was endothermic. And so considering what we talked about with how much activation energy and which one of those reactions can more or less go on its own, remember that it's the negative delta H that finds itself in the favorable realm, and the positive delta H, the endothermic condition, that is unfavorable. So notice that if we're just looking at things qualitatively, you would expect that the sign of delta S and delta H would be opposite. Until we get some other variables involved, like temperature, this is pretty much all we can assume. If no temperature is given, we just have to assume that delta H and delta S are opposites. If we have temperature, then we can calculate something else that's called Gibbs free energy, or delta G, which is really the end-all and be-all of determining what's favorable versus unfavorable. And you can bet there'll be a video on that shortly. So hopefully that was helpful, and go forth and don't tell your mom I said you could have a messy room.